Let's look at this problem here. We have a cube measuring 100 millimeters on a side, floats upright in water with 60 millimeters submerged. What is the mass of the cube? So our cube, I'm only going to draw the picture from the side. So down here is our water. This is our cube. We're told that 60 millimeters is submerged. That means 40 millimeters is not. Getting a little lag again on my computer. Sorry about that. All right, so floating. I know there is a buoyancy force upwards. I know that has to equal the mass of this block. I'm going to call it M sub O for the object. So that buoyancy force upwards has to be balancing out the weight of the block downwards. Otherwise, it wouldn't be floating. So floating, those two forces are balancing out. And we're trying to find the mass of this cube. So we actually want M naught. And I keep pushing all sorts of different buttons. Sorry about that. All right, so the next thing I want to do is I know our basic fundamental equation for buoyancy is density of our fluid, volume displaced, so the amount of the object that is in the fluid, times G. So I can say the density of this fluid times the volume of the block in the fluid times G, our equation for buoyancy, has to equal the mass of this object times G to balance those forces. All right, so the mass of this object, this block, has to equal the density of the fluid times the volume of the block that's in the fluid, because it has to equal the weight of the fluid displaced. So volume in. The cube itself was 100 millimeters on the side. Now we have 100 millimeters times 100 millimeters times 60 millimeters. So the dimensions going into the board, into the screen, and this way are still 100 millimeters. The difference is this height of 60 millimeters. We will want those measurements to be in meters so that we get our volume in meters cubed. So 0.1 meters times 0.1 meters times 0.06 for the height. This will be the volume that is in. We're told that this cube is floating in water. Its density, which I can get off the test notes, 1,000 kilograms per meter cubed. Our volume will be 0.1 times 0.1 times 0.06. That will be in meters cubed, so those units of meters cubed are canceling. So the mass of this cube is 0.6 kilograms. Now, side note, there's two things that went on here. This on the right was our fundamental equation for buoyancy. This equation's in the test notes. The force of buoyancy is always equal to the weight of the fluid displaced. This portion, where we equated the buoyancy force to the weight of the block, is from Newton's second law. F net is equal to 0. Well, it's equal to ma, but since this object was floating, it did not have an acceleration, so the net force needed to be 0. So equating the upward force to the downward force. Oftentimes in buoyancy problems, both approaches, the fundamental equation for buoyancy as well as looking at net force, are often both required to solve a problem.